Okay, welcome back. We're on chapter 8, and we're making these videos short so that you can only watch them if you need them. And this next thing we're going to talk about is understanding how risk for a single asset is measured through the standard deviation. Okay, so when we talk about the standard deviation, we need to look at what we did with the scenario analysis. And now, instead of, say, just assessing a probability for a particular event, and we'll see that on the next slide here. Okay, you can see here we've got a discrete probability distribution that gives us probabilities that each one of these particular events will occur. Okay, so if we look here, there's a 50% chance that this asset will earn its expected return of 15%, a 25% probability that it'll earn 13%. That's the pessimistic case. And then a 25% chance that it will earn that 17%. And that was asset A we looked at. So now, instead of assuming that each probability is, or at least we're assuming the probability here that each event will occur. If we go back to asset B, there's a 50% chance it will earn its expected return of 15, 25% probability of that pessimistic return, and then 25% that it'll earn the optimistic return of 23%. Okay. Now here we're going to engage in risk measurement, and we're going to assume that we might assume that we have a continuous probability distribution. Okay. So here, asset C, you can see here, this is the probability of different returns. Okay, 11 at the lowest, 19 at the highest for the most part. Now remember, these tails go on forever, but that's what we've got. For asset D, you can see it's flatter. Okay, there's a higher probability of getting a very low return here than there is for asset C, and also a higher probability for getting large returns versus asset C. Okay. A continuous probability distribution is a probability distribution showing all the possible outcomes and associated probabilities for a given event. Now, we can calculate a standard deviation from that continuous probability distribution and from the discrete. So the standard deviation, the most common statistical indicator of an asset's risk, it measures the dispersion around the expected value. So if we go back to that previous picture here, you can see that in both cases, the blue asset, here it's asset B, is more widely distributed around that mean. The mean is your expected return versus asset A. If we look down here at the continuous probability distribution, you can see that asset D is more widely distributed around that expected return than asset C. It's more tightly compact around the around the expected return. So we're going back to Norman Company, and they're looking at assets A and B. Okay. Column 1 gives the probability of each event, the pessimistic, the most likely, and the optimistic, and you can see those here. This is for asset A, that's for asset B. Then we have the returns for the pessimistic, the most likely, and the optimistic. Okay. So here, we're going to calculate the expected return. You take the pessimistic probability times its return, and that goes here in this right-handed column, which is called its weighted value. Then we take the most likely probability times its return, and put it in that third column. We do that for optimistic. So all we're doing here is we're multiplying the probability times the return for each of the three scenarios, taking those numbers, adding them together. And you can see here what we told you in the last video, that the expected return, which is equal to the sum of the probability of each scenario times its return, is equal to the expected value of a return, R bar here. And we do that for both assets, and you can see they're both 15%. So the expected return of these two assets is exactly the same. Now, again, from the last lecture, we said that in order to get me to take more risk, you've got to give me a higher return. So if these two assets both produce the same return, I'm going to want to pick the one that has the least risk associated with it. Okay? So for that, we're going to calculate the standard deviation of the returns. What we do here is for each return, okay, most likely, least likely, pessimistic, most likely, and optimistic, we take the return you get from that investment, subtract out the expected value, which was 15%, then we square it, and we multiply it by the probability of that scenario. Sum them for the three different scenarios in this case, and then take the square root of that, and that becomes the standard deviation of the return. So we'll do that for Norman Company's assets A and B. If you look here, I've got asset A. J sub 1 is the pessimistic return. 2 is the J is 1 for the pessimistic, 2 for the most likely, and 3 for the optimistic. And then I've got the returns here for each different scenario. This R bar is my expected return for the asset in general. So I'm going to take the return for each scenario and subtract the expected return. So the pessimistic, that's going to be negative because the pessimistic return is always going to be less than the expected or the mean return. So 13 minus 15 is negative 2%, and we're going to square that. Then we're going to take 15, which is the most likely return, subtract the mean, we get 0. 0 squared is 0. Then we're going to take the optimistic return of 17%, subtract the mean, and we'll get a positive 2%, and then square it. We take each one of these squared deviations about the mean, the return for that scenario minus the mean return for the asset, and we multiply it by its probability. So the probability of a pessimistic event is 0.25 times 4%, that's 1%. 0 times 50%, or 0.5 probability, is 0. And 4 times a 0.25, or 25% probability, is 1. Then we add those two together. That's our variance. And we're going to take the square root of the variance, and that becomes the standard deviation. So the standard deviation of returns for asset A is 1.41. Then we do it for asset, this should say B here, asset B. The pessimistic return for asset B was 7%. 7% minus 15% is 8%. We square that and get 64%. The return for the most likely scenario or event is 15. Subtract 15%, you get 0. 0 squared is 0. So we're just doing what we did up here for asset B, and remember that should say B. Then we take the optimistic return of 23%, subtract 15, we get a positive 8%, square it. That's 64%. So these are the deviations of these returns about their means squared. Then we take each deviation about the mean squared and multiply it by its probability. The probability of a pessimistic scenario was 25 or 0.25 or 25%. 64% times 0.25 is 16%. The squared deviation about the mean expected return for the most likely scenario is 0. 0 times 50% or 0.5 probability is 0. Then we do it for the optimistic case. That's 64%. 64% times 0.25. That gives us 16%. We add these two numbers and we get a variance of 32%. The standard deviation is nothing more than the square root of the variance. So we take the square root of 32% and we get 5.66%. So with these scenarios and an expected return of 15% for both investments, we have a number here that we could use to say that investment A carries the same return, but comes at a lower risk than asset B. So all other things being equal, asset A would be the better choice here. Now, when we look at returns and risk, we can use historical returns. We can now use the standard deviation as a measure of risk to assess the historical investment return data in table 8.1. Excuse me, 8.5 repeats the historical nominal average returns in column 1 for these three different types of bonds: treasury bills, treasury bonds, and common stock. So if you look here, the average nominal return between 1900 and 2011 is 3.9% for T-bills, 5% for bonds, 9.3% for common stock. The standard deviation of those returns are as follows: 4.7% for the treasury bills, 10.3% for the treasury bonds, and 20.2% for the common stock. And that's column 2. A close relationship can be seen between the investment returns and the standard deviations. Investments with higher standard deviations give you higher average nominal returns. Okay, stocks have the highest returns at 9.3%, which is more than double the average returns on a treasury bill. At the same time, stocks are much more volatile with a standard deviation of 20.2, more than the 4.7% that we get from the treasury bills. Because higher standard deviations are associated with greater risk, the historical data confirm the existence of a positive relationship between risk and returns. That relationship reflects risk aversion by market participants who require higher returns as compensation for greater risk. So in the next video, we're going to look at this normal probability and what we can do with it when we're assessing risk. Thank you.